So in this study, we have 15 people, in fact 15 females, 7 of which are classified in group 1, which is the control group, and 8 are in group 2, which is the treatment group. Now, the treatment in this case is a group of 15 female football players, and we're looking at the effects of a novel hamstring strength training exercise called the Russian belt. So these people in group 2 have received the Russian belt over a number of weeks, and the group 1 haven't. And we've measured 2 strength variables. One is peak torque of knee flexion with the isokinetic dynamometer running at 60 degrees per second. And the second one is 1 RM on a leg curl machine. So this is a two-way mixed ANOVA. It's mixed because one of the independent variables pre and post is time, having 2 levels, and the other one is group, also having 2 levels. But the grouping variable is a between group because we have different people in the control group compared to the treatment group. They're not the same people. Okay, so it's a two-way mixed ANOVA. Let's look at the data by plotting a graph. 2 options here. You need a graph that's going to plot mean values. So that's either a bar chart, which in this case would be this one, or a line graph, which in this case would be this one. You can either double-click the graph or you can drag it, whichever. Okay, well let's start. Let's have a look at a line graph. So I need to take my grouping variable here, and I'm going to select that as the different colors of the lines, one for control group and one for treatment group. And I'm just going to run a graph on the measurement of the peak torque, the change in peak torque. So I'll select those and I'll drag them across to the vertical axis. I'm going to need error bars, and the default error bar is a 95% confidence interval. When you've selected it, you'll need to select apply, otherwise they won't appear. Now you see that they've appeared on this schematic representation. It's not real representation, just schematic. The next thing you can do, and now you can do this sort of stuff afterwards once the initial graph has been created, and edit it afterwards, or you can do some work now. It's entirely up to yourself. If you want to do some work now, things like the names of the axes, any alterations that you want to make to the scale of the axes. So for example, the vertical axis, so I've just selected the y-axis here in the Elements Properties window, which is, if it's not appeared, you can get it by clicking this here. The minimum at the moment is set at 0, but I know that these values are up around 80. So what I might do to zoom in is to select a value of 75 and click apply. And then also the actual label at the moment for the vertical axis is just mean. I'm going to change that to knee flexion peak torque, and its SI unit is Newton meters, force times distance. Okay, that's a measurement of torque. So again, I need to click apply. Okay, if I look at the x-axis, there's no label for that, so I'm going to call that group, and again apply, just check. So this is something that's, I've noticed this happens occasionally. We've made a change here to what the vertical axis was, but despite me editing it, it's now gone back to what it was. Let me try that again. Again, apply. That's still group. That's okay now. Okay. And the line itself, so we've got display error bars. The only other thing I would suggest you do is take off the footnote. It's a default setting. It just takes up space. And also, I wouldn't bother with titles, etc. Normally, when doing manuscripts, the journal editors want you to have titles, etc. outside of the graph, and usually at the bottom, not at the top, which is where these would be placed. So, just before I click OK, I just want to check I've got everything I wanted to. That all looks good. Here we go. Right. Okay. As soon as it's worked. So there's our vertical axis, deflection peak torque, Newton meters, and group. And we've got a key here demonstrating which of the two groups we've got. So what can we deduce from this before we do a little bit more editing? It appears that the control group hasn't really changed over time. They're around about 79 on average Newton meters and 79 afterwards. So normal training hasn't worked very well at all. It's certainly not increased their hamstring strength. However, visually at least, I need to provide further evidence with some inferential statistics. We can see that there's been an increase over time in those that received the Russian belt. So we can see that the pre-score on the treatment group, those that received hamstring, were around about 80 Newton meters, and after the training that they've gone up to around about 85 Newton meters, showing an increase. I will want to do a bit more editing here. So to do that, if you double click the graph, and things I would say to change is the background, is change that either to white or transparent, and also get rid of the border. So we end up with a graph that looks like this at the moment. I would also suggest that these lettering are probably a little bit small. So let's make some changes to the size of that font. Again, to do that, whatever you click, double click it, and it will send it into an edit function. Go into number format in this case. Wait a minute, that's not correct. Number format, I want font. My mistake. I've selected the axes rather than the number. That's better. Text style, here we go. Let's make it 10. There we go, it's gone a little bit bigger. Similarly, I'm going to do that for this as well. Apply. Both of the axes are in bold, that's good. The only thing that you don't get from the default setting in SPSS with these line graphs, which we prefer, is that the actual mean values, which are these, they're not there, as in it's just the ends of the lines. What I'd actually like to see is some symbol indicating the mean values. So one approach you can take is to actually add these now. And to do that, if you go to this radar button here about add markers, so the markers in this case we're referring as the mean values of the groups. And we've got 4 groups in total here. So if you click that, okay, you'll notice that 2 little circles have appeared on each of the groups, okay. But I'd like there to be a differential between these. So rather than in this case being 2 circles, I would prefer squares and circles. Okay, so what you need to do is this new elements group that we've created for the markers, because previously all we'd got was the error bars and the lines. We've now got our markers have appeared, having selected this radar button, is here for style, select shape, click apply. Now we've got a differential between circles and squares, which is better. Okay. Also what appears when you do that is this tab appeared. You'll notice when it was on border and colours. Oh, well, sorry, it wasn't there before, but you can't get rid of it now, it is there now. So there we go. Sorry, we've gone into an edit function, let's go back. So we've changed the fill, so let's make it black in this case. I can change the size if I wanted to. Well, I would have done if I was in the previous diagram, previous window, but that's disappeared now. So let's click back to this and mark it. Now I can change it. Yeah, now I can change it. 8, what does 8 look like? Pretty big, maybe a little bit too big possibly, but at least it stands out. So I think pretty much that's it. If you want to, you could change, what would it look like if I changed the weighting, how thick the line was. Close. I think, yeah, well, anyway, you can play around with it. I might not need this because I might actually have this with it. Normally when you have a key indicate the different groups, you actually have that within a paragraph underneath the graph. So to get rid of the key, the legend, do that. So that is there or thereabouts. Okay, so let's close that. Just an additional point I've realized is if you look at the vertical axes that you're running in every count of 5 Newton meters, you might want to increase the level of sensitivity there about how it looks. So you could change that from every 5 to, let's say, every 2. And I might centralize the graph a bit better. It could be at 72, let's say. What would that look like? There. Okay, close. Okay, so I think that gives it a little more sensitivity, so resolutions regarding these mean values. So there's our graph. Now, to get that into your Word document, all you need to do is to highlight it, right-click, and copy special. Okay, and make sure that the JPEG is initialized and go OK. Then in your Word document, just go paste special, right click image, and it will just place the image there for you, and then you can change the size by pulling on the diagonal. Don't pull on because you'll change the aspect ratio by changing these things here in your Word document. Always, if you want to change the size, do it from the diagonal. So that's our graph. It appears that there seems to be an improvement because of the Richard belt. Let's do the analysis now. So firstly, we need to check for normality of distribution. So as our grouping variable, and at the moment we're looking at peak torque. Select that into the dependence list. Plots, I wouldn't bother with such a low sample size, it's almost meaningless to look at the shape of the distribution. That's the button I want to check for normality of distribution, this sort of bell-shaped curve. So can I assume normality? So there's an actual statistical test. 2 in fact are run. I suggest looking at the Shapiro-Wilk because you've got low sample sizes, somewhere less than 30 or so. We've got 15. All of these values here are greater than 0.05. So the result of that means that we must accept the null. We can't reject the null. And the null test in this case is that the raw score that we've got for each of these 4 groups, the raw data, compared to its normal equivalent, is it different? And the answer is it's not different, because the null is, the null case is there's no difference. So there's no evidence to reject that hypothesis. So in our case, that's good because we have normally distributed data. Well, we have evidence for normally distributed data. Then we can push on and actually run the analysis, which in this case we have to select repeated measures designs because one of the independent variables is a repeated factor, and we'll call that time, and it's got 2 levels, pre and post. Select the dependent variables that we want to analyze. I also suggest that you put group into the between factor. That's the other independent variable. Ask for descriptive statistics, and also the other parametric assumption apart from normality is homogeneity test. Continue, and that's it. So, first question, did we have equality of variance? So that's Levene's test. If these values are greater than 0.05, you have evidence, at least you don't have evidence to reject the null, which is, the null in this case is that your data, the sample from which, the populations from which the samples have been drawn are in fact the same in terms of variance, which is what we want. And so that's the null the null we have to accept, good, that's what we need. So that's our assumptions done with. So then the question is, well, was there an effect of Russian belt training over time? So that's where we look at this interaction term group, which is obviously the treatment control group over time, and the answer is a p-value which is less than 0.05. That means we reject the null. The null is that there's no difference. We reject that. There is a difference. In other words, there's an effect of Russian belt training on peak torque, isokinetic peak torque. Okay. Finally, what we'd like to know is, we've seen from the study and the analysis that we've done so far, is that there is in fact an effect of Russian belt training on hamstring strength, and that there's an increase in strength. We can see this change, and we've done the statistics to support it. What I don't know is the size of that effect. There are a few ways in which we can do that. We can either ascribe a percentage change. So we know we've got a figure of just over 80 kilos here for the pre-score on the treatment group, and it changes to just over 85, so around about a 5 kilo difference. 5 kilos as a percentage change of an initial score of around 80 is about 6%. So there's been a 6% increase in strength of the hamstrings. The other approach which you should also do is to calculate one of the indexes of effect size from Jacob Cohen's research, and we can use Pearson's correlation coefficient little r. To do that, we need to find some information, which is the F score and the degree of freedom for the error term. So we can calculate little r, and we can use Jacob Cohen's interpretation of little r as follows. So any r value greater than 0.5, we can say there's a large effect. Between 0.3 and 0.5 is medium, and between 0.1 and 0.3 is small. Anything less than 0.1 is negligible. Okay, so we need to find out where these values are in order to calculate the effect size of this interaction, this change over time. And so we get those from the within subject contrasts that the computer has run. So this table here. So for the treatment by time here, which is basically group by time, we have an F score of 24.4, and the error term degree of freedom is 13. Okay, so if you take the equation, we put 24.4 in here, and here we put 13, and we do the square root of all that. Okay, and if you do that, you'll get an R value of about 0.81, which therefore a result of that is it's a large effect. Okay, so in summary, what we found is that Russian belt was effective at increasing hamstring strength over the standard exercise regime that these female footballers were following. That created about a 6% increase in change, and that change was a large effect. Okay, that's it. So to finish off, in order to sort of write the results, what we found is that there was an effect of Russian belt training on peak isokinetic torque of the hamstrings at 60 degrees per second, and then you've got some numbers there relating to the F statistic. The first number in the brackets there, the number 1, relates to the degrees of freedom of the model term, and the 13 is the error term. The F value itself is 24, and then you've got the P value, the probability, the significance value, less than 0.01. And then what I've done there is then sort of give some mean values for the post scores of the Russian belt training group, around 85.6 after training, standard deviation, compared to the control group post scores. And then the corresponding R value for the interaction term. So it's a large effect, in other words, and I've also interpreted that effect as what percentage increase you've seen in the treatment group. Okay, so you have everything you need there.